This is a lesson on bonds. A quick overview. There are ionic bonds, which is where electrons are transferred, opposites attract, so you got a positive and a negative charge attracting each other. And when the two opposites come together, you get a lower energy than if they were separated. One of the key things on this is bonds. Why do bonds happen? Bonds happen because you get a lower energy. Why would something not bond together? Because it has a higher energy. So it's all about the energy and getting a lower situation than you had before. This would follow Coulomb's law, which is charge 1 times charge 2 divided by r squared. And there's a constant in there. But the size of the charges and the distance between them gives you the force of attraction between the particles. Here's a quick overview. Covalent. Covalent is caused by the mutual attraction of an electron cloud by two different nuclei, two different atoms nuclei. So here we have a nucleus, here we have a nucleus, and we have an electron cloud. There's an attraction between the electron cloud and that nucleus. There's an attraction between that nucleus and the same electron cloud. So even though the two positives don't really want to be, they're attracted to the same electron cloud. It's kind of like a love triangle going on here. A diagram of this, if you have zero energy, if you're way, way, way far away, kind of like up above, there's, they're ignoring each other. If you're really, really, really close together, the nuclei are too close and they go, get away from me. Somewhere in the middle, there is a optimum lowering of energy. This would be your bond length. The distance from here to here would be the optimum distance where there is the most attraction, therefore lowest energy. Again. And then the last quick overview, polar covalent. Polar covalent is where the electron cloud is not shared equally. The electron orbitals not shared equally. One atom is more pulls the electron cloud closer to it than others. HF, hydrogen fluoride. This is the positive end. This is the partial negative end. Greek letter delta lowercase. That means the electron cloud hangs with the fluorine more than the hydrogen. Now there's no flip the switch. This is it. This isn't it. Again, this gives you the lowest energy. Permitted that situation. The key indicator on what type of bond is more prevalent is electronegativities. Electronegativities is the relative ability of an electron to attract shared electrons. It's the ability of an atom to attract a shared electron pair. These are found experimentally using magnetic fields. It's an entirely arbitrary thing. It's a ratio, so there's no labels. Somebody had to pick the most electronegative, which is fluorine, which is a 4.0, and this is a college, so that's why they said 4.0. The noble gases tend to be darn close to, if not equal to, 0. General broad paintbrush things, the difference in electronegativity, where you take the two atoms' electronegativities and subtract them. The difference in electronegativities can range from 0 to mid-range to high. The bond type in general tends to be covalent. There is pure covalent, and that's the only thing that we can say that's absolute. This would be polar covalent, PC, polar covalent, and this is ionic. Now there's no cutoff. It's not like day, night, off, on. It gradually gets more and more ionic as you go this way. You get more and more covalent as you go this way. The homework in this book doesn't even cut off things. They just say which rank these in order of more ionic to more covalent. So they even say, is this an ionic bond or something like that? It's probably a better way. We probably shouldn't do it in real kid chemistry. Put electronegativities together with molecules. Molecules are made up of atoms, and each pair of atom has their own variance of attraction for the electron cloud. So to do that, you get something called a dipole moment. Again, put it in with the magnetic field. You can, now that you've had vectors, most of you can look at it vectors. It depends upon the geometry of the molecule and the electronegativity of the atoms being joined together. If you have carbon dioxide, what you do is draw an arrow. So this is the positive end, has a little plus sign there. This is the negative end. If it's like this, then you can tell that the arrows are equal and opposite, so the dipole moment is 0, which means it's going to be a nonpolar molecule. If you have something like water, oxygen is more electronegative, so if you add the vectors like this, and if you add the two vectors together, you get overall arrow going this way, where this is the positive end, and this is the negative end. That would tell you that this is a polar molecule. Ions, a little bit more depth. General with formulas, really quick thing, most of this you know. Formulas, you have the metal forming the cation and the non-metal forming the anion. Positive charge, negative charge, the opposites attract. You lose enough electrons to lose or gain electrons to gain noble gas configuration. And then you have enough of one ion or the other to balance, add enough ions of each sort to balance charge. Say you have an iron 3 plus and an Cl 1 minus, you need 3 Cls to join together. Size of the ions is important to know. Positive ions tend to be small, negative ions tend to be big. It's important to do it. It's kind of difficult to interpret what the size are, because when they fit together, you get sort of a pattern, and you got to have enough positives and negatives in the lattice, and we'll talk about that in a later thing. Some ions will fit together better. Some ions are more difficult to fit together. But essentially, the key thing is you alternate positives and negatives in a lattice. If you have a 1 plus ion, if you remove another one, it would shrink because there's more protons and the size gets smaller. If you have a 3 plus ion, it'd be smaller. So the more positive the ion is for the same row, same period, it gets smaller. And the reverse is true if you have a negative ion. If you have a 2 negative ion, it gets larger because you have more and more electrons running amok, and the protons cannot come up and come up with it. Bond character. What is the difference between ionic and polar covalent bonds? It's really tough to tell. There is absolutely no pure ionic bonds. There's always some sharing going on, theoretically. There are pure covalent, hydrogen, diatomic, things like that. That would be covalent. There are pure those, but not pure ionic. The book goes through a bunch of steps to kind of show you what's going on, but empirically, that means you test it. If you dump in water and it conducts electricity, it's ionic. So if it conducts, if a solution conducts electricity, then it's ionic. If it does not conduct electricity to any perceivable amount, then it'd be polar covalent. Again, we're making assumptions, simplifications, massive things that we're doing just to make it work. The key thing is, if you get a lower energy with a bond, that's the key idea. If you have lower energy, you'll form a bond. If you don't get a lower energy, you will not form a bond. So it's all about trying to figure out why, puny human brains trying to figure out why this happens when you get a lower energy state than before. There's a useful handout or page on the book that you can use later on. Next up. Next up is Lewis dot diagram.